In this presentation, I'll be explaining alternating current AC circuits with resistance only, and then AC circuit with inductance only, and then alternating current AC circuits with capacitance only. Coming to the contents of this presentation, first AC circuit with pure resistance. This is the AC circuit with a pure resistance. We'll be explaining that one. Then AC circuit with inductance only. And the third, we'll be explaining what is the alternating current circuit with capacitor C only. So the resistance on circuit, AC circuits, and inductance or inductive AC circuit, and AC circuit with capacitance only. Now let us see alternating current circuit with pure resistance R. Now this is a circuit, the AC input voltage, and that's connected to a resistor. And this is the equation for that one, and corresponding waveforms I am shown here, same as this one also, corresponding waveforms, voltage and current. And here also it's a voltage and current, and this is a voltage waveform and this is a current waveform. Both are in phase, and the voltage equation is that V equal to Vm into sin omega t. This is the voltage that is applied here, V equal to Vm sin omega t. Now the current that is flowing through the resistance, that is equal to Im sin omega t. That is, both are in phase. There is no phase shift between voltage and current in a pure resistive circuit. Therefore, the current I equal to Im sin omega t, where the Im, the maximum value of the current, equal to the maximum value of the voltage Vm divided by the resistance. Therefore, voltage and current both are in phase, and in order to calculate the power, we have to multiply the instantaneous voltage and instantaneous current. Then we'll be getting from 0 to pi radians that for this cycle, the half the cycle of the voltage, you can say that both voltage and current, they are in positive. Therefore, the product voltage and current will be positive. That is why you're getting a positive power from 0 to pi. Again, from pi to 2 pi, we can see that one voltage is negative and current is also negative. The product of negative into and negative, it will be again positive. Therefore, the power consumed by the resistive load is again positive. Therefore, the third, this one, the curve or that waveform, that represents the power. So this is the voltage, this is the current, and this is the power consumed by the pure resistive load as such. Now, if you see the resistive circuit here, power consumed will be calculating, the average value of the power consumed will be calculating, and that will be getting, of course, the Vm Im divided by 2, or Vm by root 2 into Im by root 2, or it is equal to the RMS value of the voltage and RMS value of the current. So the product of RMS value of the voltage and RMS value of the current is the average power consumed by the pure resistive load, and will be derived in the equation later. And in this case, this is of course the power, and if you, the shaded portion represents the energy. It is a product of the power and the time, which represents the area. Therefore, this shaded portion represents the energy, and if you distribute the power over this much time, or if you distribute this energy of this time period, we'll be getting the average power, which is equal to Vm Im divided by 2, or Vm by root 2 into Im by root 2, or RMS value of the voltage and RMS value into RMS value of the current. That is the average power consumed by the load. That will be appearing as a heat here. And if you see, looking into the phasor diagram, if you draw that, this is the instantaneous voltage and instantaneous current. Both are in phase in the pure resistive circuit. If you see the phasor diagram, the voltage vector is this one, and this is the current vector. Both are in phase. And as you know that one, the voltage vector is rotating at, if for example, frequency equal to 50 Hertz, this is rotating at a 50 cycles per second. And both are in phase, and this is that in the case of a pure resistive circuit. Voltage vector and current vector, they are in phase, and that is rotating at what the frequency is that. If for example 50 Hertz frequency, that is rotating at 50 cycles per seconds. Now calculating the power consumed in a pure resistive circuit. Power consumed, as I told you, it is the product of instantaneous voltage and instantaneous current. For example, P is equal to Vm sin omega t into Im sin omega t. That is the equation for the voltage and equation for the current. Then we'll be getting it is equal to Vm Im sin squared omega t. Again, I can put it as Vm Im divided by 2 into 2 sin squared omega t. or 2 sine squared omega t can be represented as 1 minus cos 2 omega t, or Vm Im divided by 2 into 1 minus cos 2 omega t, or we'll be getting, expanding this one, we'll be getting Vm Im divided by 2 minus Vm Im divided by 2 into cos 2 omega t. Therefore, the power in the equation for the power, you can say that there is a fixed component Vm Im divided by 2, and there is a fluctuating component Vm Im divided by 2 cos 2 omega t. Therefore, the average value, to calculate that one, we can say that average value of this fluctuating component, that will be 0. That if you integrate this one from 0 to 2 pi, this value will become 0. Therefore, the average power will become the Vm, this is a fixed one, that is fixed component, which is equal to Vm Im divided by 2, or which is equal to Vm by root 2 into Im by root 2, or the RMS value of the voltage into the RMS value of the current. That is the average power consumed by the resistive load, which is equal to Vm by root 2 into Im divided by root 2. And therefore, this Vm by root 2, one representation is that capital V, which is equal to RMS value of the voltage, and Im by root 2 equal to the RMS value of the current. V into I, that product, that is in watts, unit of power is in watts, V into I. Another way of representing is that you can represent V equal to, as per the Ohm's law, V equal to I into R. Or replacing V by IR, we can get power is again equation is that which is equal to I squared R. Power V into I, or it is equal to I squared R. One more equation is that P equal to, we can replace I by V by R, or again P can be written as V by R into V, or V squared by R. So the three equation is that P equal to VI, or P equal to I squared R, or P equal to V squared by R, where V equal to RMS value of the voltage, which is equal to Vm by root 2, and I equal to RMS value of the current, which is equal to Im by root 2. Therefore, the power is appearing as a heat production, heat that is appearing as this one. Another definition for power factor, for the power factor, if you look into that one, since the both voltage and current, they are in phase or phase angle equal to 0, the power factor equal to cos phi or cos 0, which is equal to 1. Therefore, it's a unity power factor. Pure resistive load means power factor equal to unity. Another way of definition of power factor is equal to cos phi equal to the active power divided by apparent power, or P by S. In this case, you can say that one, both, since there is no reactive power, apparent power is same as active power, or power factor equal to P equal to S, or power factor equal to unity. For a pure resistive load, power factor equal to unity. Now let us see an AC circuit with inductor only. So for say AC circuit, Vm sin omega t, that's connected to an inductor having the inductance value L, and this is the you can say that let the voltage across this one inductor, or that supplied voltage, is equal to Vm sin omega t, and voltage across the inductor, as you know the well-known equation, the voltage across inductor V equal to L di by dt, V equal to L di by dt, or we can say that V by L equal to di by dt, or if you expand this one, we can get di equal to VL into dt, di equal to VL into dt, or dl equal to V by L into dt, V by L into dt, di, or the current can be, you can integrate di and you are getting current I equal to 1 by L integral V dt, 1 by L integral V dt, or again V is beyond as Vm sin omega t. So substituting this Vm sin omega t here, we will be getting I equal to 1 by L integral Vm sin omega t dt, or we can take it is equal to Vm by omega L, omega is coming here, Vm by omega L cos omega t, of course there's a negative sign is there. Therefore, minus Vm by omega L cos omega t, or Vm by omega L into minus cos omega t. This minus cos omega t can be written as it is equal to sin omega t minus pi by 2. Therefore, the equation for current can be written as Vm by omega L into sin omega t minus pi by 2. Therefore, current equal to, that's Vm by omega L is represented as Im. That is the maximum value of the current. In an inductive circuit, the maximum value of the current is equal to the maximum value of the voltage divided by omega L, which actually inductive reactance omega L. Therefore, Vm by omega L, which can be written as inductive reactance XL. Therefore, that is represented as maximum current Im into sin omega t minus pi by 2, meaning that the current is lagging the voltage. If you're looking into equation 1 and 2, the current is lagging the voltage by 90 degree. That is why if you see the waveform here, the voltage waveform is the current is lagging the voltage by 90 degree in the case of a pure inductive circuit. Or in order to calculate the power, that you can multiply the instantaneous voltage and instantaneous current here. For example, if you calculate from 0 to pi by 2, the voltage is positive and current is negative. That is why you can getting a negative power. From pi by 2 to pi, both voltage and current are positive, then you will be getting a positive power. And from pi by 2 to 3 pi by, from pi to 3 pi by 2, we'll be getting the both voltage is negative, current is positive. Therefore, you will be getting a negative power. Now here you will be getting both are negative. Current and voltage are negative from 3 pi by 2 to 2 pi. Both the power is positive. Now we will be getting this is the positive power and this is the negative power. Or during the positive power, energy stored in the inductor, that is this area that represents the energy stored in the inductor, and this area is the energy is released from the inductor. For the average energy, if we say average, if you calculate the average area here, that will become 0, or we can say that average power consumed by the inductor equal to 0. Now coming to the phasor diagram, as we already seen that if the phasor diagram, this is the voltage vector, current vector is lagging the voltage vector by 90 degree. The vector is rotating in this direction. That's rotating at 50 hertz. For example, 50 hertz frequency means 50 cycles per second it is rotating. But at any instant we can see that voltage vector is leading the current, or basically we call it as current is lagging the voltage vector by 90 degree. Therefore, this is a phasor diagram of a purely inductive circuit, and this is the instantaneous voltage, current and power diagram. And we have seen that instantaneous current equal to Im sin omega t minus pi by 2, and where Im equal to Vm divided by omega L. Omega L we call it as 2 pi fl, or that is called the XL, or inductive reactance, Vm divided by XL. And XL equal to 2 pi fl, which is called inductive reactance, which is the unit is equal to again ohms. Inductive reactance is equal to ohms. And expressing the impedance as a complex quantity, this can be represented as R can be as a complex quantity. We can say that here the voltage vector is leading the current vector by 90 degree. In that way, it is represented as Z equal to J into XL. That as a complex quantity, it is represented as JXL. Suppose since the voltage vector is leading the current vector by 90 degree, it can be represented as JXL. So that is the impedance representation is JXL for a purely inductive circuit. Now continuing the AC circuit with an inductor only here, same as we have seen. This is the AC circuit with inductance L only here, and this instantaneous voltage, instantaneous current is lagging the voltage by 90 degree. If you take the product of voltage and current, you will be getting a negative power here, a positive power here, negative power here, positive power here. The area under this power, that is called the energy, and here during this period, positive side the energy is stored in the inductor, and during the negative side energy is released from the inductor. If you take the average, if you if you take the average of this area, that will become equal to 0, or meaning that average energy equal to 0, or energy consumed by the inductor, pure inductor, it is equal to 0. Therefore, as same thing shown here, and this one during this positive period, as we can say that energy is stored in the inductor. During the negative period, energy is released from the inductor. Therefore, the net energy for one cycle, it will be equal to 0, or of course the power consumed by the inductor over one cycle, it is equal to 0. Therefore, it is an energy storing element only. There is no power dissipation for the ideal inductor. And if you see the phasor diagram, again as we have seen that the voltage vector and this is the current vector that is rotating at 50 hertz, 50 cycles per second, but at each instant we can see that voltage vector is leading the current, or we can say that current is lagging the voltage vector by 90 degree. So this is a phasor diagram of a purely inductive circuit. Now let us see the power consumed in a pure inductive circuit. Of course, as we have already done, it is equal to 0, but it is a mathematical proof is that P equal to instantaneous voltage and instantaneous current. As such, we can say that instantaneous voltage equal to Vm sin omega t. And current, as I told you, the current is lagging the voltage by 90 degree. Therefore, Im sin omega t minus pi by 2. Take the product of that one. We'll getting Vm into Im sin omega t. Of course, here sin omega t minus pi by 2 will be the cos omega t. Of course, minus sign is the, or it is equal to Vm Im divided by 2 into 2 sin omega t cos omega t. Or P equal to, we can say that it is equal to Vm Im divided by 2 sin 2 omega t. average power for one cycle, if you take the average value of this average power is equal to average of sine omega. Since average value of the sine 2 omega t equal to 0, we can say that average power consumed by the inductor, that's equal to 0. Hence, the power consumed by the pure inductor over a one complete cycle P equal to 0. Therefore, the average power is equal to the P by M, Vm divided by 2 into the average value of the sine omega t. Average value of the sine omega t over one cycle equal to 0. Therefore, the average power consumed over one cycle equal to 0. Hence, the power consumed by the pure inductor over one complete cycle P equal to 0. Of course, the power factor, as you see that one, cos phi, which is equal to cosine of the phase angle between the voltage and current, cos 90 degree, of course, lagging actually. Based on the current is lagging the voltage by 90 degree. Current vector is lagging the voltage by 90 degree. Therefore, the power factor is equal to cos phi equal to cos 90 lagging, or cos 90 is equal to 0, or set P. It's called the 0 power factor, 0 power, set P of lagging. 0 power factor lagging in the case of a pure inductive circuit. Another way of definition of power factor is the ratio of the active power to the apparent power. Active power equal to 0. In a pure resistive circuit, there's no, pure inductive circuit, there's no active power. Therefore, it is equal to again equal to 0. Another way of defining the power factor is that active power P by S divided by apparent power, that's equal to again 0. Therefore, the power factor of a purely inductive circuit equal to 0. And of course, this is as we have seen the phasor diagram. Voltage vector is leading the current, or you can say that current is lagging the voltage by 90 degree. The vector is rotating in here. This one is rotating at, for example, 50 cycles per second. At any instant, we can see that voltage vector is leading the current, or you can say that current vector is lagging the voltage by 90 degree. Therefore, this is a phasor diagram of a purely inductive circuit, and this is the instantaneous voltage, instantaneous current, and instantaneous power of a purely inductive circuit. The average power consumed by an inductor equal to 0 over one cycle. Now let us see the AC circuit with capacitor only, C only. Same as we have seen in the inductor case. Here, the Vm sin omega is the voltage, that is the applied voltage, and that is applied across a capacitor value C. And here, in order to calculate the current and voltage, here voltage is taken as Vm sin omega t. The voltage is equal to Vm sin omega t. As you know that the current through a capacitor is given by C dV by dt. Current through the capacitor is equal to C dV by dt. Or substituting this, taking the derivative of this voltage with respect to time, we will be getting C d by dt of Vm sin omega t, or Vm omega c into cos omega t, or cos omega t can be written as omega t plus pi by 2, or this Vm omega c, that is equal to the maximum current Im. Therefore, this one equal to Im sin omega t plus pi by 2, where Im equal to Vm by Vm omega c, which is equal to Vm divided by 1 by omega c. 1 by omega c, we call it as the capacitive reactance Xc. 1 by omega c, or 1 by 2 pi Fc, that is called capacitive reactance Xc. Therefore, the current, maximum current I equal to Vm divided by Xc, which is equal to 1 by omega c. This is the maximum current Im, and thus the current I become, that is equal to Im into sin omega t plus pi by 2. Therefore, V equal to Vm sin omega t as per the equation 1, and as per the equation 2, I equal to Im sin omega t plus pi by 2, meaning that the current is leading the voltage by 90 degree. Therefore, here if you see that one, this is the voltage, instantaneous voltage, and this is the instantaneous current. You can see that one current is leading the voltage by 90 degree. Then again you can calculate the product of instantaneous voltage and instantaneous current. You will be getting the power. Therefore, if you positive voltage and positive current, you will be getting a positive power. If you get here positive voltage and negative current, you will be getting a negative power. Again, you will be getting here both are negative, therefore the positive power. Again, one is negative, you will get negative power. Therefore, this is the power diagram in which this is a positive power we are getting, negative power is getting, positive power is getting negative. Now, if you take the area, that is represent the energy one, the average, if you calculate the average of this area, that will become 0, or average energy or average power is equal to 0 over one cycle of a capacitor. Therefore, average power consumed by a capacitor is also equal to, pure capacitance is equal to 0. Therefore, Xc equal to 1 by omega c, which is equal to 1 by 2 pi Sc, which is called the capacitive reactance, and the unit of that one is equal to omega. Therefore, expressing the impedance quantity in a complex quantity. In that one, we can get it as Z equal to minus JXC. Previously, it was in a inductive circuit, Z was plus JXL. But in capacitance, it is equal to minus JXC. The reason is that in this case, the current vector is lagging the, sorry, the voltage vector is lagging the current vector by 90 degree. Or can say the current is leading. Of course, the voltage vector based on the voltage, because impedance equal to voltage divided by current. Therefore, we can say that one voltage vector is lagging the current vector by 90 degree. That is why, since lagging means that if it is lagging, it is minus j. Normally, plus j, if it is say anti-clockwise direction rotation, is the plus j. If there's a clockwise rotation, is equal to minus j. If you, in this case, we can say that one I is, of course, V voltage vector is coming, or current is leading, or voltage is lagging. Therefore, the impedance corresponding to the pure capacitance is equal to Z is equal to minus JXC. J represent 90 degree shift. Plus J represent 90 degree rotation in anti-clockwise direction. Of course, minus J represent plus 90 degree rotation in the clockwise direction. Therefore, this is a phasor diagram of a purely capacitive circuit, and the instantaneous voltage and instantaneous current, the product we will give the instantaneous power of a capacitive circuit. And continuing the AC circuit with a capacitor C only here. Again, the same circuit is shown here. As we have seen, the instantaneous voltage and instantaneous current are there. You take the product of that one, you will be getting a power. And this is a positive power because both voltage and currents are positive. Here a negative power is there since the voltage is positive but current is negative. Therefore, the power is negative. Again, here you can say that both are negative. Voltage and current are negative. Then you will be getting a positive power. Again, here we can say that current is positive, voltage is negative. Therefore, we are getting the power equal to negative. For the, as we have seen in this diagram, the shaded portion that represents the energy, it is other product of power and time, which is called the energy. Therefore, here a positive energy. This is actually the energy is stored in the capacitor, and here energy is released by. Therefore, this negative energy means energy being released, and here positive energy means energy being stored in that one. Therefore, if you say, if you take one cycle, the average value of this area or the average value will become 0. Therefore, the average energy is equal to 0, or average power consumed by the capacitor is equal to 0 in a pure capacitive circuit. Again, this is the phasor diagram. You can see that one current vector is leading the voltage vector by 90 degree, and the voltage vector is this is rotating at this direction. Of course, the anti-clockwise direction at 50 hertz per. If it is 50 is the frequency, 50 cycles per second. Now let us calculate the power consumed by a pure capacitive circuit. Power, as we have seen, power is equal to the voltage and the current product, Vm sin omega t into Im sin omega t plus pi by 2. Since the current is leading the voltage by 90 degree, Im sin omega t plus pi by 2. Take the product of this one, we'll be getting Vm into Im sin omega t into, of course, sin omega t into this one is cos omega t, sin omega t into cos omega t. Or we can say that we'll dividing the Vm by Im divided by 2. Again, 2 sin omega t cos omega t. Or 2 sin omega t cos omega t equal to sin 2 omega t. Therefore, the equation for the power by multiplying these two will be getting Vm Im divided by 2 into sin 2 omega t. Now, the average power can be calculated from this one. It is the average Vm Im divided by 2 in the average value of the sin 2 omega t. If you take the average value of sin 2 omega t, that's equal to 0. The average value of the sin 2 omega t, that is equal to 0. Or if you are substituting that one, we'll be getting the average power over one complete cycle equal to Vm by Im by 2 into 0. Or the average, hence the power consumed by the pure capacitor over one complete cycle equal to 0. If capacitor is pure, then power consumed by over one cycle is equal to 0. Because you can say that one Vm Im divided by 2 into average of 2 omega t. Average of 2 omega t equal to 0. Therefore, the average power consumed by the pure capacity over one complete cycle equal to 0. Same as we have already explained that one. During this one, energy being stored in the capacitor. During this 0 to pi by 2, energy is being released. Again, here energy being released. Here energy being, or the energy being stored in the capacitor. If you take the average of that one, if you take this average of this area, you can say that that will become 0. Therefore, that is why we can say that power consumed by the pure capacitor over one complete cycle equal to 0. Or looking into the power factor, as you know that power factor is the, of course, one definition is the phase angle between voltage and current, cosine of that one. Therefore, it is equal to cos phi, which is equal to, since it is 90 degree, current is leading the voltage by 90 degree, we can say that cos 90 leading. Cos 90 is again, it is equal to 0. 0 power factor leading. Therefore, it is a ZPF leading. We call it as ZPF leading. If the capacitive load, pure capacity load, power factor equal to ZPF leading. Another way, again, that based on the, apparent power and real power, we can say that again real power equal to 0. That is why the power factor equal to 0. Therefore, the another way of looking into the power factor. Therefore, the power factor of a pure capacity circuit equal to 0. We call it as ZPF, 0 power factor leading. Therefore, again, this is the phasor diagram as I already explained. Current vector is leading the voltage vector by 90 degree.